up. So logarithms, and we've seen them before. The initial reason logarithms were created, if you like, were to do calculations with large numbers. Because, of course, we're talking about the days before calculators were around. And so they'd change things into bases. So a number would be, well, common logarithms were 10 to the power of something. And whatever that power was the logarithm, basically. And that's why it came up with laws, like when you want to multiply two numbers together, you would add the logs, because what you were really doing is multiplying 10 to the power of that number. And as we know with indices, when you multiply, you add the powers. And that's where all the log laws come from. They are the inverse of exponentials, logarithms. So they're the opposites of each other. And if y is equal to a to the power of x, so a could be any base you like, then x is the log of y, base a. So notice the base doesn't change. The base is the constant number. And one is the opposite of the other. So the exponential is y equals a to the power of x. So when we make x the subject, we do the opposite, and that's when it becomes a logarithm. So x becomes the log of y. We're going to look at base e a lot. That gets used a lot in our work. Now, e is another irrational number, just like pi. It's around about 2.71727? Something like that. So x then becomes log y. That's known as the natural logarithm. The natural logarithm. There are other ways of writing it. lny, you might have noticed that button on your calculator. You might have thought it meant in, but it's not the in button. It's actually ln for natural logarithm. And the reason it's ln and not nl, again, that's to do with the French, because they're funny the way they speak. They don't say natural logarithm, they say logarithme naturel. And log y, if you don't see a base written down, we would assume it's a natural log that they're talking about. Interesting thing about that is go back to the 70s and beforehand, if we got in our little time machine, and we saw log y, we would assume it was base 10. That used to be, because that was the standard one everyone used. But once we started using calculators, natural logarithms became the standard that people use. So now when we see log without a base, we assume it's the natural logarithm we're talking about. Okay? So natural logarithm is base e. Let's draw a log curve. Voila, there it is, in all its glory. That's one where the base is greater than 1. Just like all exponentials go through the y-axis at 1, because this is the opposite, the inverse, all logarithm curves would have an x-intercept of 1. So in other words, the log of 1 is always equal to 0. The upside down one would be if the base is in between 0 and 1. You don't have logarithms of a negative base, same as when we're dealing with exponentials. We don't say negative 2 to the power of something. It doesn't work. We stick with positive numbers. And the interesting things we like, domain, well, we can see from our curve there, is x is greater than 0. And the range is all real y. Let's have a look at the log laws. As I say, logarithms are the opposite of indices. So you find your log laws are like the backwards of the index laws. We have an index law that says when we multiply, we add the powers. So with our logarithms, when we add them, we multiply. And remember, m and n, they're sort of like they're not the powers. So it's not true to say we add the powers, multiply the powers, but when we add the logs, we multiply. So log m plus log n, mn. And just like when we're dealing indices, it only works if the base is the same. Subtraction becomes division. This is the one we found very handy when we were solving those exponential equations, you may remember, where we logged both sides. And that allowed us to bring the power to the front. So if you have the log of m to the power of n, you bring the n to the front, and you get n log m. The log of 1 is always equal to 0. That's similar to the index law that says anything to the power of 0 is always equal to 1. So it's the other way around. The log of 1 is always equal to 0. Log a base a will always be 1. Because remember, the base is a, and the way we read a log is we say a to the power of the answer will get us the log. So a to the power of 1 is A. Now, because exponentials and logs are opposites, if you have an exponential where in that power there is a log, if the bases are the same, they will cancel. So a to the power of log a will cancel and will just leave us with x because those bases are the same. And this is what's often called the change of base law. So say you've got a logarithm in base a, but for some reason you want to work with a different base, you can change the base and we just rewrite it as the logarithm of that new base, but we have to divide it by the log of the old base. And that's how we change it to a new base. All right. So x equals log 125 base 5. Way of thinking about this is 5 to the power of what is equal to 125. That's how we read it. And sometimes people like to actually change it into that exponential equation and say, oh, right, so 5 to the power of x is 125. Well, 5 cubed is 125. So x would be equal to 3 for this one. Log 343 base x is equal to 3. So this is saying x to the power of 3 is equal to 343. So x cubed is 343. Cube root of 343. Oh, 7. There you go. 7 it is. Same sort of question. It's just that they haven't said x equals. Evaluate. So log 16 base 4, we're saying 4 to the power of what's 16? Well, 4 squared 16. So if I wanted to do it and make it really obvious, because if they said show that it was equal to, and I had to put the steps in, well, then what I'd do is, I'll change 16 to 4 squared, and then I've got that rule that says I can bring the power to the front. So I've got 2 log 4 base 4. Oh, but then we've got another rule that says log a base a is always equal to 1. So log 4 base 4 is 1. Very long way around of just getting the answer 2. But if you had to show some sort of working, I mean, they're the sort of steps, I guess, I'd put down. 6 to the power of 2 log 3 base 6. Now, I can't cancel these straight away because I haven't got 6 to the power of log. I've got 6 to the power of 2 log. So I need to get that 2 back into the log. So now it becomes 6 to the power of the log of 3 squared base 6. I can cancel now. 3 squared, 9. Okay. Adding logs, we can combine these together. They're the same base. 16 times 8 is 128. So 2 to the power of what's 128? 2 to the power of 7 is 128. So we get 7 as our answer. In this case, we could have worked it out anyway, because I could have said, well, look, 2 to the power of 4 is 16. So log 16 base 2 would have been 4. 2 to the power of 3 is 8. So log 8 base 2 would be 3. 4 and 3 is 7. I could have done it that way. But sometimes we get ones that we can't just work out, like this one. I mean, 10 to the power of what's 125? It's not nice and neat. 10 to the power of what's 32? Again, not nice and neat. 10 to the power of what's 4? No good. So I'll combine it all into one log. The addition means multiply. So I've got 125 times 32. The subtraction means divide. So that's divided by 4. Tidy that up and I actually get a nice neat number I can work with in this case. So 10 to the power of what's 1,000? Well, 10 to the power of 3 is 1,000. 7 to the power of what's 8? 7 to the power of what is 2? Again, can't work that out. But I don't have a log law that says, when I divide, I subtract. It's the other way around. But if you look at this closely, it's actually in the form of a change of base, but it's in the form of the answer. If I go back the other way, I could rewrite that as log 8 base 2. And then I do know 2 to the power of 3 is equal to 8. And so the answer is 3. So it's actually using that change of base law in reverse. The log of the square root of 1/8. Well, can I write the square root of 1/8 as 2 to the power of something? And what would that power be? Oh, close. 3 on 2, 3 on 2. So I actually took the half out first. So I brought the power of a half out the front. And then 1/8 is, of course, 2 to the power of -3. So there's our -3 on 2 is our answer. Okay, exponential equations. If I can rewrite them as the same base, exponential equations, of course, are very easy. And 1 on 27, I can rewrite as 3 to the power of something. 1 on 27 is 3 to the power of -3. So in this case, I could just equate the powers. 2x plus 1 is -3. There's my answer, -2. But where the logarithms became useful is when I can't do that. I can't rewrite 9 as 2 to the power of something. And so we use this idea, okay, well, let's log both sides. That then allows me to bring the x to the front of the logarithm. And so x log 2 is log 9. Divide both sides by log 2. There's my answer, log 9 divided by log 2. It doesn't matter what the base is. It can be any base you like, as long as it's the same base. And could only approximate this one, but around about 3.17. So you'd find, if you went to your calculator, 2 to the power of 3.17 won't exactly be 9, but it'll be very close to 9. Okay, exercise 12A. Ooh, and 6B, question 8.